We're going to continue talking about the atom and more specifically kind of the beginning of quantum mechanics. Okay? Last week we talked about the wave and what the wave looks like in the electromagnetic spectrum. Today and the remainder of this unit talks about quantum mechanics. Again, quantum mechanics is all about where is the electron in the atom. This is where we left off the last time, and that the wave nature of light doesn't explain why that's happening. Okay? Something else that we'll look at later. So, to begin talking about, Max Planck tried to explain where those electrons were. We do know that the electromagnetic spectrum for an atom is unique, the line spectrum. And it kind of, in a way, intrigued these physicists because they were lines that they could say that they had a certain energy. They have a wavelength, they have a certain frequency based on the fact, the speed of light. And now it's like, why do we see that? Well, Planck says that the energy comes from packets of energy called quanta. And that these packets of energy, or quanta, are like stairs on a staircase. As you go up the stairs, you have more energy. Now, to give this some sort of realistic, humanistic qualities, you can think of it this way, as you go up the stairs, there's more potential of a hurt factor, so to speak. If you fall off of the first stair, it is not going to hurt very much. There's not going to be a lot of energy transferred from you falling and hitting the ground. Walk up 2 stairs, now that energy is increased. You walk up a flight of 10 stairs, at the top of that, the potential of that hurt factor is going to be higher. Falling off of a flight of 10 stairs as opposed to just 1. And it's this idea of potential energy that Max Planck gives us quanta, that there's this potential energy that's there, that these light packets are giving us. If you have a ramp, the energy increases as well, but it doesn't increase in nice steps. A continuous spectrum is a ramp, because you have to walk up. Now, some people walk upstairs one at a time. And then some people bound up the stairs as fast as they possibly can. You can skip stairs doing that. Therefore, there can be energy skips in those light quanta that we see. In 1905, Albert Einstein explained through experimental data, and that's an important thing, it's always important with experimental data, that light can be described as quanta of energy. So he gives us, in a way, proof that atoms actually exist. 1905, we finally get the definitive thing. We already know about the subatomic particles, but they needed something else. He says that light quanta are considered to be photons. This is one of 5 papers Einstein is accredited for writing in the year 1905, or being published in the year 1905, which is quite an accomplishment among science. Having 5 papers published in 1905. And again, so he does give us, this is the Nobel Prize winning stuff, this information. And it is called the photoelectric effect. And that you have this radiant energy hitting a metal surface that forces the electrons to move, and that they move towards a positive terminal. Now, how this is done, it is based on that energy, and that's how they're able to determine how much energy using the current, using Planck's constant, which is the H, meaning if you see an H, that's it is Planck's constant by the frequency. Okay, so Planck's constant times frequency, that's the nu, that's the V, tells you the energy. This is the Nobel Prize winning work of Albert Einstein. Not what everybody thinks it is. Everybody thinks that Albert Einstein gets the Nobel Prize for E equals mc squared. And even that, the equation is not fully said. There's more to it than that. However, this is what it is. The photoelectric effect is what he wins the Nobel Prize for. Most everything else is theoretical. So, Einstein's winning work does help us out a lot. And it explains the why we see the line spectrum. We can calculate the energy of one photon packet. We can even, in some ways, begin to see other things. If we do some basic substitutions, we can see, based on just some algebraic substitution, if we solve for the frequency, we can make some substitutions that energy is equal to Planck's constant times the speed of light divided by the wavelength. Now we can kind of see maybe better where maybe Einstein gets his idea of E equals mc squared. And by the way, it took a woman to figure out what that actually means of any significance. So, girl power. And now for my favorite person, Niels Bohr. Dalton gave us a atomic theory based on a lot of people's thoughts and ideas. Niels Bohr also follows along that similar path, takes people's data and finishes the puzzle from it. And developed his model of the atom. So now we have the hard sphere model, which sometimes seen as the Dalton model or the Democritus-Dalton model, the plum pudding model, the nuclear model, which gives us the nucleus. Then Niels Bohr gives us his model of the atom. Like Rutherford, uses experimental evidence to kind of justify, because they kind of need that now. Can't just say, here's the model of the atom. Trust me, I'm smart. Doesn't work that way. Uses that electromagnetic spectrum. That includes all types of radiation, X-rays, UV light, ouch, don't touch, IR, microwaves, radio waves. And he believes that the electromagnetic radiation behaves like a wave. It is through Niels Bohr and his model of the atom that we get our first indication of the location of electrons. And it is, again, based on the data that is collected from the electromagnetic spectrum, the line spectrum, and the fact that these behave as waves. So, Bohr's model says that the electrons orbit the nucleus just as planets orbit the sun. Now, each electron has a different amount of energy depending on which orbit it was in. The orbits closer to the nucleus have lower energies. Talked about that earlier. The stairs, how much energy they have. And those further away have more energy. The orbits are quantized. Means that they could only be found at those distances from the nucleus and never in between. So Bohr's model, he doesn't say that the nucleus is not there. He says it's there. I'll just draw some little positive charges in there. Maybe we'll get some neutrons going on here. Okay, hanging out. Now, Bohr says that the electrons orbit the nucleus, just as planets orbit the sun. Coincidentally, Bohr's model is known as the orbital model. Hence the emphasis on the word orbit on this slide. So Bohr says that these electrons that are here have a certain energy to them. They have less energy than the electrons that are on the outside of the nucleus. The farther away you go, the more energy they have. Where they are doesn't really tell us that. But we do know that they have energy. Now they can change the location of the orbit, but it takes a nudge for that to happen. They do not get to hang out in between and not kind of be willy-nilly kind of like, oh, I don't know where to be. No, it's there. You have a orbit. You don't just get to hang out in between orbits. Okay? You have to know where you're located because it's based on that energy that we saw. When they are in their lowest possible energy, they are in what's called their ground state. Just as they the hurt factor I described earlier, going up the stairs, when you're on the ground floor, it's not going to hurt. Well, it might, but it's not going to hurt as much when you fall. Less energy. Ground state, lowest possible. As you go up, it requires energy. And it requires you to be in an excited state. It's that nudge for an electron to move its orbit. That is called a quantum leap. And it has nothing to do with the TV show from the early 90s. When they fall back, when they go from an excited state to a ground state, there's a certain amount of radiation that's given off in the form of heat and or light. The higher the leap, that is going to then change how much energy has been given off when it goes back down to a lower energy. Farther the drop, more energy. Now it doesn't have to go back down to the lowest energy, it just goes down in energy.